Hello everyone, welcome to Academy. I am Dr. Nandita and today I am here to solve some problems based on the concepts that you have learned in the chapter Some Basic Principles of Organic Chemistry. So basically you know about the catenation property of carbon. So basically carbon is having catenation property due to which it can combine any carbon atom of other elements. Also covalently. Also it is possible for carbon atoms to be covalently bonded with other electronegative elements such as oxygen, hydrogen, sulfur, phosphorus. And that's why a separate stream of chemistry which is known as organic chemistry has been generated. So basically I am not going to discuss in detail about the basic principles here, but let's move on to the problems. But organic compounds are playing important role in our body processes or some biological processes, and it is not only industrially important but in our day-to-day life. Without these organic molecules or compounds, we cannot run our day-to-day life easily. So it's very important to know about the basic principle of organic chemistry. Now with this, let's start the problems. Problem 1 is asking which of the following molecules does not show stereoisomerism. So I hope that you have understood or you have learned about the concept of stereoisomerism. So with this concept I am going to solve this problem, right? So we have 4 options for this. The options are 3,4-dimethyl hex 3-ene. Option B is 3-methyl hex 1-ene. Option C is 3-ethyl hex 3-ene, and option D is 4-methyl hex 1-ene. One by one I will draw the structure of these molecules and then we will see which of these or which of the molecules does not show stereoisomerism. So let's start with A. So we have hex, so we will have 6 carbon atoms here. So let's draw the structure first. So 3,4-dimethyl. So this is 3 and 4 position. We will have 3,4-dimethyl groups and hex 3-ene. So here. And C is 3, CH2, CH2, CH3. This is nothing but the 3,4-dimethyl hex 3-ene, right? So this one is able to show geometrical stereoisomerism. Because of the presence of chiral center, right? So what is geometrical isomerism? Because it is having 2 identical methyl groups side by side, so it will show either cis or trans kind of geometrical isomerism. So it will show optical or stereoisomerism which is geometrical in nature, right? Let's see for B, 3-methyl hex 1-ene. Again we will have 6 carbon atoms and 3-methyl. So here our methyl group would be here. 3-methyl hex 1-ene. Here our ene for the first position. So this is our 3-methyl hex 1-ene, and also this is a chiral carbon center. That's why it will also be able to show optical isomerism. Right? this is also able to show optical stereoisomerism. Let's see for C. 3-ethyl hex 3-ene. Ethyl. So in third position we will have C2H5 group and hex 3-ene. Here we will have a double bond. Right? So this is our 3-ethyl hex 3-ene, and if you see carefully, this molecule will not show any chirality, so it is not having any chiral carbon center, not showing any chirality, and because of optical inactivity, it won't be able to show stereoisomerism because it is not having any chiral carbon center in this structural morphology of this molecule. So because of not having the property of chirality, no chiral center, it will not show optical isomerism or any kind of stereoisomerism because of the optical inactivity. Right? So we have already got our answer, but let's just check the last one, that is 4-methyl hex 1-ene. Hex 1-ene. It will also have a chiral carbon center here, so it will show also optical isomerism or optical stereoisomerism. So what we have seen here, molecules A, B and D are having chiral centers, either 1 or 2, and they are showing stereoisomerism, either geometrical or optical. But the organic compound C, because of the fact it is not having any chiral center, it won't be able to show any kind of stereoisomerism because of the optical inactivity of it and because of the absence of any chiral center to it. So we have got our option. The right option is option C. I hope you have understood. Now let's move on to problem number 2. Problem 2 is asking which of the following compounds is not chiral. So chirality basically can be defined as the property of any molecule or compound which is not identical to its mirror image, or the mirror image cannot be superimposed onto it. So one chiral center must have 4 different groups attached to it. So basically this is the concept of chirality. So with that we would like to solve the problem. So let's check for the A. 1-chloropentane. So we have 5 carbon atoms in pentane and CH3, CH2, 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 and here it will be CH2Cl because it is 1-chloropentane. And from the structural point of view, we can say that it will have no chiral carbon atom. No chiral carbon atom for this molecule, right? So we can already say that that this compound is not chiral. Now let's check for the other option. Option B is 2-chloropentane. So again we will have 5 carbon atoms and this is our 2-chloro. So CH3, CHCl, CH2, CH2, CH3. This is our 2-chloropentane. So if you check, this is our chiral center. So it is having chiral carbon center, 1 chiral carbon atom in this compound. So it is not, it will show chirality. Now let's see for compound C, 1-chloro-2-methyl-pentane. So 1-chloro-2-methyl. This is our 1-chloro-2-methyl-pentane. Also it will have 1 chiral center which is indicated here. So 1 chiral carbon center or 1 chiral carbon atom in this compound as indicated in C. What about D? 3-chloro-2-methyl-pentane. So 3-chloro, so we will have chlorine here and 2-methyl. And if you check carefully, you will see that there are 2 chiral carbon centers. So it will show chirality. So this is a chiral molecule, right? So 2 chiral carbon atoms for this molecules. So now if you check the options, you can see that only compound A is not showing any chirality and other compounds that is indicated in options B, C and D, they all are showing chirality. So they are chiral compounds, but option A, that is 1-chloropentane, is not a chiral compound. So our option A is the correct option for the problem. Simple. Now let's move on to the problem 3. Problem 3 is asking that which amongst the following is the strongest acid? So what we know from the theoretical portion or theory part that we have learned already, that for a strong acid, it should be stronger if it will have a stable, it will form a stable conjugate base in presence of water, right? So this is the concept of that. So if you check the molecules carefully, you will be able to see that this CH3, CHCN whole thrice, it will form the most stable conjugate base among the given acids in this problem. So it will form the most stable conjugate base which is CN whole thrice C minus. This is the most stable conjugate base among the given compounds for CHCN whole thrice, right? Now, what will happen? This conjugate base can have very strong minus I and minus R effect, and it will be stabilized by several or many structures or which are actually resonating structures, right? So we will draw these resonating structures and we will show that the conjugate base of CN whole thrice CH, that is CN whole thrice C minus, is the most stable among the given options. So, we are going to draw this resonating structures, resonating hybrid structures, right? So, CN whole thrice CH, carbon will have a delta minus charge and hydrogen will have a delta plus charge, which will be in equilibrium to break in the following manner. CN, C triple bond N here, or it can be drawn in a different way, maybe in bottom. Yeah, here. C triple bond N here, and carbon will have a minus charge here and it will break with H plus as well. So, this is our conjugate base. So, I am drawing the resonating structure. So, this will go here and this will go here. So, this is giving you CN whole twice C double bond C double bond N with a minus because it has moved here, and now here you will have the strong minus R effect from this CN, and also here strong minus I effect, because of the fact that these resonating structures are getting stabilized, and also this is giving you the most stable conjugate base for CN whole thrice acid, right? Now, you can also draw this one in the following manner, that CN, or maybe this way, C double bond N, C double bond N, C double bond N, and they are stabilized in this manner. This is the resonance hybrid structure of the conjugate base CN whole thrice C minus. Because of the resonance hybrid structures, as I have presented here, this conjugate base is the most stable conjugate base among the given acids. So, from this problem we can say that among the following, the strongest acid is CN whole thrice, because it is forming the conjugate base which is the most stable one because of the formation of such resonance hybrid structure, and also due to the strong minus I and minus R effect of CN groups, right? Simple. Now, let us move on to the final problem of this short lecture. Problem 4 is to synthesize 1.0 mole of 2-methyl propane 2-ol from ethyl ethanoate. How many equivalents of CH3MgBr reagent will be required? Integer value we have to put. So, first let's write down the equations, or to understand how many equivalents of CH3MgBr reagent is required to prepare the ethyl ethanoate. To prepare the products here, that is 2-methyl propane 2-ol from ethyl ethanoate. So, let us first write down the reactant, that is ethyl ethanoate, CH3 C double bond O OC2H5. This is called ethyl ethanoate or ethyl acetate. Right? Now, if it is reacting with the first equivalent of CH3MgBr reagent, how the reaction will take place. So this anion will hit here, it will go here, it will come back here, and this bond will break. So what then it will produce? It will produce CH3CO CH3, that is nothing but acetone, right? So we have already used one equivalent of CH3MgBr. Now we have to get this product, or this is our desired product. So let's use another equivalent of this same reagent, that is CH3MgBr. So this one again will hit here and will give you, this can be happened in presence of water. So what we will get? CH3, COH, CH3, CH3, and we have obtained our product, that is 2-methyl propane to all. So how many equivalents we have used? Here is our one equivalent and here is our two equivalents. So we have used two equivalents of the reagent CH3MgBr to get 2-methyl propane to all from ethyl ethanoate. Very simple. So with this I would like to end this short lecture. I hope you have enjoyed, and for more such lectures you have to get connected with Abdemi. Get connected and get registered with Abdemi. Thank you very much. Have a good day. See you soon. Bye bye.